There we go.
Here we go. The weekend was okay. Did you get some?
The weekend was interesting.
Yeah.
We had an interesting adventure with a neighbor dog.
Neighbor dog.
Yeah, who decided he would rather live with us than them. And it was a
you guys
Labradane,
a
Labrador Great Dane hybrid.
A Labradane.
A
Wow.
Labradane.
I don't think I've ever seen one around.
The biggest darn puppy you ever saw.
Right.
Huge dog. Wonderful. Wanted to come play with our dogs. Can I be your dog? And we took him back on Saturday. He showed up Saturday, and he was just hanging out on the porch on the front couch on the front porch. It was fine, but he started chewing on some of the furniture. We're like, no, not okay. And then we realized he's just a baby dog, but we took him back. Then Sunday morning, 6:45, our dogs are barking, and who's at the front door but the neighbor dog again. So we took it back. We felt very bad because he was like, no, I'd rather live at your house.
Yeah, I've bonded with you.
Yes, kind of. Yes. And they're not home all day, and somebody's here all day, and we have other dogs, and it's obviously more fun here.
Wow.
But yes, indeed.
I've heard that Facebook's had some problems today. So
really?
Yeah.
Well, I haven't heard much about that. I was busy teaching. We did a very fun activity. I would love to do this with people on one of our programs, but we would need outdoor space, and I would need I don't know, maybe I could do it from down at your store, and we could do it out in the parking lot.
Yeah.
But it takes about 30 people to do it. And it's definitely an outdoor activity. And we were modeling the Earth-Moon system. And so we took a 10-inch inflatable vinyl ball for the Earth, and 10-inch Earth means the model stand-in for the moon is a cue ball, 2.5-inch cue ball. And then we went ahead and we took string and modeled the orbital distance, and we had the students stand in a big ring, and we got 28 of them to stand in a circle. And of course, with 28 of them, and they're standing equidistant apart, that's how far the moon travels each day. And we were talking about why you can't fly directly to the moon, why you have to do the Hohmann transfer, and why does it take 4 days to get there, and so on and so forth. So we were basically doing all this really cool stuff. And the students were like, oh, rotation, revolution, why does one side face the Earth all the time?
Right.
Does the moon actually rotate? What's synchronous rotation? What causes it? What's libration? Why is it there? And by the end, they're like, oh, yeah, we get it. And I said, so, because I've had people tell me, oh, well, you can't teach that to ninth graders, sixth graders, fourth graders. I said, how many people are convinced they could teach this to third and fourth graders? And they were all like, oh, me. I said, there you go. My very first interview for a teaching job. I'll tell you that after the interview.
I guess there is no Facebook.
Using data from NASA's Fermi Gamma Ray Space Telescope, scientists have recently discovered a gigantic, mysterious structure in our galaxy. This never-before-seen feature looks like a pair of bubbles extending above and below our galaxy's center. These enormous gamma-ray emitting lobes aren't immediately visible in the Fermi all-sky map. However, by processing the data, a group of scientists was able to bring these unexpected structures into sharp relief. Each lobe is 25,000 light-years tall, and the whole structure may be only a few million years old. Within the bubbles, extremely energetic electrons are interacting with lower energy light to create gamma rays, but right now, no one knows the source of these electrons. Are the bubbles remnants of a massive burst of star formation? Leftovers from an eruption by the supermassive black hole at our galaxy's center? Or did these forces work in tandem to produce them? Scientists aren't sure yet, but the more they learn about this amazing structure, the better we'll understand the Milky Way. The better we'll understand.
Well, hello, everybody. This is Scott Roberts from Explore Scientific, and I'm here with Dr. Daniel Barth, and still trying to figure out what the heck happened with Facebook. So, we're glad that you're watching on YouTube and Twitch. I have to reconfigure Twitter because Twitter has ended their program with Periscope. So that's a different deal. But we have our YouTube channel has grown over this year, and we really appreciate it. And some tell me that YouTube has a better viewer experience anyway. So there you go. But hey, I like Facebook too, so because I belong to all those astronomy groups on there, which makes it really easy to interact with them. So sorry to anyone who might have wanted to watch it on Facebook, but I'm sure that they'll get back online. Mike Wiesner says some employee at Facebook may be looking for a new job. A change was made at the company that took all their servers off the internet several hours ago. Both internal and external servers are offline.
Oh,
I don't even know how they could do that.
That sounds like they've had a hacker attack or something. That doesn't sound like somebody tripped over a plug and pulled it out of the wall.
Oops. That's right. Yeah, I guess. I would imagine that the senior executive staff there is not very happy right now.
Yeah, Zuck's probably screaming at them over the speakerphone as we speak.
Right. Let's recognize some of the people that are watching right now. We have Steve, who is also known as Book. Okay. Martin Eastburn says howdy from East Texas. Sky might be okay tonight late. Cameron Gillis is watching. Becca Hautala. Martin Eastburn. We talked about Mike Wiesner. Steve says he generally ignores Facebook. Not the biggest fan. Okay.
I do business there.
Yep. And Celtic Ravena. I always get it messed up. Twitch doesn't care about user experience. Oh, wait, never mind. It's Twitch. I think they do, so. An employee, Mike says an employee edited the DNS record. Holy smokes. Oh, my God.
Yeah. Hi, you're unemployed.
Yeah. Wow.
Oh, dear. Hi, you took the whole company out.
He might not ever get an internet job again.
Probably not.
I don't know. Unless he gets really famous and, he could do like a talk show circuit,
The guy took down Facebook.
Yeah. And then they'll make a movie about him and, you know, and they'll give them a free ride on the 0G plane, and then SpaceX will
stop
fly
now.
them up for free as well.
Incompetence should not be rewarded like that. I'm sorry.
Yeah.
Not when there are good
somebody
people
like-
like me and you, Scott, who do our job right and work hard, you know.
Yeah, but, you know, I've messed up things before too.
Oh, no.
Sure.
No.
Sure, yeah. I've made tons of mistakes. My life is it's like a, you know, it's a list of mistakes, you know.
Punctuated equilibrium. Things go along smoothly, then the asteroid strikes.
That's how I learned. That's how I learned,
It's
dude.
blown to hell.
That's how I learned. So you picked an interesting topic about galaxies, and whenever, all the time, I think you're going to exhaust what you need, you know, what you can say about galaxies. But
oh no!
And then you surprise me. So here we are with the 1984 discovery of ultra-diffuse galaxies.
Indeed,
Yeah.
indeed, and you know, Scott, that as we look out into space, we look back in time.
Yes.
And so sometimes it's interesting to see what it would be like if we were out at a distant place in space. And so if we were out in the Jalise star system, you know, famous lots of planets. And of course, here we go. If you were watching you and I from Jalise star system, which is about 35 light years away.
Oh, yeah. Wow, look at that. And you look like
that's what I look like when you and I met.
Cowboy. You know, I was looking at I like, you know, sometimes you're searching for things on the internet.
Yeah.
And I ran into something about the Dalton gang and Eureka Springs and stuff like that. And one of those guys looked just like that. You know,
Not me.
so.
But that's the way Maurice didn't like me to wear my hat when I was at the store.
Why is that?
Oh, no, that doesn't look like a professional salesman, Dan. But I will take that. But yeah, that's me from about 35 light years away. So the farther away you get, the better I look. That's
Yeah. Now you think that Daniel's teasing Maurice, but he did kind of sound like that. So.
No, he did. He did.
Yeah.
He had this wonderful, rich accent and very, very interesting way,
Yeah, kind
very
of real
persuasive,
deep
very deep in the chest, and kind of a interesting cadence, an extraordinarily persuasive speaker. Oh my God, he would have no trouble selling, you know, ice cubes to Eskimos, as the old saying goes. Absolutely.
Ketchup popsicles to ladies in white gloves in August.
Kind
right?
of, yeah. He absolutely was a very persuasive man. He never I was one of his best sales guys. He never understood me because I would always talk to people and find out what they needed, try to teach them about the hobby. They would get more interested. They would come back for more stuff. No, make the big sale. I'm like, but no, I want people to be customers for a long time. I want them to be an astronomer for life.
Yeah.
They may never come back in. You have to get them to open their wallet now. And
there's a couple of philosophies on that. One is that, you know, you're just trying to sell whatever you can for as much as you can, as quickly as you can, you know, and then the other way is that you realize you have someone that, especially in our scenario, we have people that are embarking on a
lifetime
journey, right? And so you're not selling a used car. You're
bringing someone into the
them.
club.
Yeah, you're outfitting them. So, but there are people that will argue with me on you know, those sales approaches. So, but
yeah, I don't know. Anyway, so enough fun with that. Coming back to our topic, the ultra-diffuse galaxies. One of the big astronomical observatories that's participating in this is the ALMA, the Atacama Large Millimeter Array. And ALMA was in the news again this week. They've found the first, what do they call it? Circumtriple planet It's a planet orbiting stably in a 3-star trinary system,
Wow.
which I would have said that wasn't possible, but they have detected it. And the other interesting thing I've noticed is, as I've been looking at more data with galaxies, is the current trend now is to say, okay, let's go look at several different telescopes. And so let's take the Hubble image of a certain object, and then we'll take an image from the Large Millimeter Array, and then we'll take a look from the Chandra X-ray telescope. And they're taking images from various wavelengths and various resolution telescopes, and they're combining them together to make one image, and it's color-coded for wavelength. And so this new astronomy, where we're actually merging images, and of course, it's computer processing power makes this possible, because before, say 10 or 20 years ago, the idea that you would take 2 images of, say, the Andromeda Galaxy from different telescopes, and you would combine them, merge them. The idea we would take frames from different instruments would just be off the wall. And, there's field curvature and field of view and et cetera, et cetera, et cetera. But new computer processing power, the last 10 years or so, powerful enough to renormalize these images, to get them to overlap smoothly and orthographically so that they make sense. And some of the images I see just in the last few years where, this is a combined image from 4 or 5 different types of telescope: gamma ray, X-ray, infrared, visual, ultraviolet. And they combine all these and they say, the infrared shows us this, the visible shows us that, the ultraviolet and the gamma ray and the X-ray all show us different things about this. And you take a look at things like planetary nebula, and you realize, wow, different wavelengths are showing us different kinds of interactions. Visible light shows us ionized gas giving off in hydrogen alpha, and sometimes dust reflecting in the visible wavelengths. But infrared is showing us things that are going on that are hidden by dust. The X-ray and the ultraviolet show us these violent interactions between the shock wave and the surrounding interstellar medium that are creating high energy photons. And so you get to see these combined images are really amazing. I'm going to share just a stunning image with our audience. And this is the cluster. And this is Abel 2744, if that means anything to you. George Abel, of course, was an astronomer who was categorizing galaxy clusters in the 50s. And in 1959, so some 3 years ago, he went ahead and published a catalog, the Abel catalog, of galaxy clusters visible from the Northern Hemisphere. And 1989, after his death, people went ahead back with comparable instruments, and they published an updated Abel catalog that now includes the Southern Hemisphere. But you take a look at this photograph, Scott, and what's stunning is that almost everything we see here is a galaxy.
The galaxy. Wow.
And so you think about what's an average galaxy, anywhere between, 500 billion and 1 trillion stars. And you look at all these things and you go, wow, how many stars are there? And
how many planets, how many moons? I mean, it's just
how many planets, right? How many moons? Our galaxy is thought to have 1 trillion rogue planets.
Wow.
They did the microlensing survey.
So they just go from star system to star system, or what?
Yeah, when star systems are forming, large Jovians are known to migrate in and out before they find a stable orbit. And so what happens, you get these tidal effects, these Jovian and Neptune ice giant class planets. They form early, and they're interacting gravitationally with dust clouds. And this Roche effect, where things are slowed down or sped up. And what happens is we had Jupiter and Saturn, we believe, migrated in, perhaps closer than Mercury, and then back out. Well, that is the elephant in the china shop. you have a Jovian-sized planet that over a few tens of millions of years migrates in and then back out again. It's going to, give the what do they call it in hockey? A body check,
Yeah.
right? Where the guy takes his hip and slams the other fella into the boards. Well, that's what these Jovians are doing to these inner planets. And the new theory is we've talked about the idea of planetary collisions before. Our moon was formed by proto-Earth being impacted by the planet they call Theia, hypothetically about the size of Mars. And the only thing is, people say, well, if Jupiter came in and nudged Theia out of its orbit and it fell inward and it hit the Earth, why didn't it just shatter both planets? The kinetic energy would have been off the charts, would have been obscene.
Yeah.
And how did the planets...
You see the animations of that, it looks like they destroyed each other.
And so now the current theory is what they call the glancing blow or multiple impact. They say, if these things are spiraling in, they're not going to collide like this or from the back like this. They're going to come in and hit a glancing blow and keep going. And the thought is that through the inner solar system, multiple glancing blows. And these glancing blows, they exchange material, but more importantly, the planet that's infalling gets slowed down. And so finally they get slowed down enough, they're sharing the same orbit, and it isn't so much a titanic impact as it is a slow merger and smooshing together. And they think that this multiple impact, glancing blow, and then a slower speed merger allows planets to merge and grow without having a cataclysmic event that destroys them. So this multiple impact thing, and these Jovians, when they wander in, occasionally something's going to get a gravitational boost. Bepi Colombo is doing this right now, right? It's going in and it's having a gravitational exchange of energy with Mercury, and it's going to eventually slow down and orbit Mercury. Well, these we did the same thing with the Voyagers, except they slingshotted them out of the solar system. And we believe that this effect happened routinely, that solar systems would have started out with 20 to 30 planets and ended up with 10. Where do the others go? They get either knocked into the sun, they get absorbed by the Jovians, right? Like a Shoemaker-Levy 9 impact writ large, or they get the boot. You get the gravitational crack the whip, heave ho, out you go. And these planets just plunge out like the Voyager spacecraft into the interstellar medium. And maybe they'll be captured by another solar system. And that probably won't be a happy event. Can you imagine if there was an Earth-sized planet that was coming in at some crazy, stupid angle? And people go, holy crap, it's going to be captured. It's going to have a sun-grazing orbit, and it's going to be captured in a 120-year orbit at an angle of 70 degrees. And it has a perihelion somewhere between Mercury and Venus, and it has an aphelion somewhere between Mars and Jupiter, and that's not going to be a happy day.
Well, hope it doesn't happen.
Well, but with a trillion rogues out there, with 1 trillion rogues out there, it could happen. And we look at this same idea. What happens in galaxy clusters, Scott? These interacting galaxy clusters.
Yeah. We're going
Would
to
you-
collide with Andromeda, right?
Right. Would you not have
the
glancing
theory.
below collisions? Would you not have tidal interactions? Would you not have exchange of material? Would you not have some galaxies being given the gravitational slingshot and get out of our group and becoming rogues?
Perhaps.
And in fact, we look at this huge cluster in Abel 2744 and estimates of about 10,000 galaxies. Different authors differ, but okay, let's take a round number. Let's say 10,000 galaxies in this cluster, and it's got to
In
have
this
a
picture,
huge,
right? 10,000 in this 10,000 in this field of view.
yeah, 10,000 in the field of view.
Okay.
And you go, okay, holy cow. Well, if there's 10,000 in this field of view, obviously doesn't enclose the whole volume. So you got 10,000 clusters, you've got a whole lot of dark matter, you've got a whole lot of cold gas and dust, and then you have the luminous matter, and you have the diffuse matter, and you have the condensed galactic matter, and you look at all this and it's gravitationally interacting. And we know that galaxies collide all the time. We know that ellipticals are the result of collisions, probably many collisions over a long period of time. Spirals are, spirals we know are cannibals. We see it with Andromeda, we see it with Triangulum, we see it with the Milky Way. The Milky Way, there are some 20 or thereabouts, dwarf galaxies orbiting us.
Mm-hmm.
I think there's more than that, but let's pick again a round number of about 20. And all of those are being devoured, incorporated into the Milky Way. We are shredding them. We are absorbing their gas. We are absorbing their star systems. There are the Large Magellanic Cloud has a light bridge between it and the Milky Way. And it's a streamer of infalling star systems and dust and gas being siphoned off from the Large Magellanic Cloud into the Milky Way. For these star systems and the planets in them, probably it's not a perceptible event. It doesn't change anything. They move, they take up orbit around one galactic mass or another. It doesn't change anything for them. Galaxies are such diffuse objects. Someone asked me, well, what happens when Andromeda and the Milky Way collide? And I said, well, really? You're talking about for the star systems? Yeah, for us. I said, nothing really. And they said, well, how could it not? How could it not? Two galaxies in collision, won't it be like the end of worlds? And I said, no, absolutely not. It's like two clouds of gnats flying over a lake and flying through each other. The odds of two gnats having a head-on collision are virtually zero. And galaxies are a lot more diffuse than clouds of gnats. You realize we're in a star cluster. The nearest star to us is 4.5 light years away. If you want to take the closest 50 stars to us, you have to have a sphere of over 100 light years in radius. They're compared to the size of a solar system, about 1 light day. No, the odds of collision are really poor. Might we be disrupted so we change our path around the galactic center? Yes. Does that really affect our immediate planetary environment in the solar system? No, it does not. But it certainly affects the way galaxies evolve. It certainly does affect the way galaxies evolve. And when we look at this, we are talking today about ultra-diffuse galaxies. So what are we talking about? Well, these bad boys were first discovered by Allan Sandage. And this is a guy who I feel should be a lot better known. Sandage, basically, he was a fellow at the Carnegie Observatory System, which includes Palomar and Mount Wilson and some others. And he did his PhD at Caltech. His thesis supervisor was Walter Baade, and famous Nobel Prize winner, right?
Wow.
And
Yeah.
he worked at Mount Wilson and Palomar. He was Edwin Hubble's graduate assistant. After Hubble dies, he takes over the observing program and continues his work after his death. And so Sandage is like, he swings a big bat, and yet he's not well known.
To me, I always
funny.
thought he was like Father Time. Like, I had the privilege of seeing him talk once at an astronomers conference, and I got to ask one question. And at that time, I was still trying to learn about the universe, and I asked him. I said, "Okay, well, let's just say that we take an imaginary space ride to the edge of space, you know." And I said, I get all the way out there, and I said, "What do I see?" You know, and I can't remember the age of the universe thinking at the time. This is early 90s or late 80s.
About 11 billion years at that time, something like that.
Something like that. And so he said, well, he says, you get out there, you fly out there, and everywhere that you look, again, you still see the same distance everywhere, 360. I was having such a hard time wrapping my head around that, because I thought, well, wouldn't we like see it like a little bit less distance this way, you know, versus that way, you know?
Isn't there a seashore to the cosmic ocean? And really there is not.
Yeah. So that's still sometimes it's hard for me to wrap my head around.
Yes.
But yeah, he was an amazing astronomer. I agree with you. I don't think he was pushed down or anything like that, but he's not as iconic as Hubble. Yet he probably did just as important work.
Absolutely.
Right?
Absolutely. Hubble died young with a lot of his work uncompleted. And Sandage, I think really Sandage's work kind of cemented Hubble's reputation after he was gone. Because he worked for decades on Hubble's project. And Hubble, at the time of his death, had surveyed, I don't know, 20-some, 30-some galaxies. And Sandage went on to multiply that work many times. And we've talked about science as a process, Scott, the idea that, oh, I have this interesting finding, and it seemed to suggest this big thing. And we've talked about this with Hubble, with Einstein, with Galileo, with Cassini. And we talked about Cassini looking at the moon Iapetus and saying, oh, I think it's hard to see on this side of the planet because one face has got to be darkened by impacts. That was never decided in his lifetime. And yet others came along and completed the work, and we named Cassini Regio on Iapetus. Why? He was the first discoverer, or the first one to come up with the idea, the Hubble constant. It might be fair to call it the Hubble-Sandage constant, but nobody, I would get slapped for that. And yet Sandage did as much work on it, probably substantially more than Hubble did. He wasn't the first. You know, we revere Galileo, but you think about it, Galileo spent his whole career proving Copernicus right. He made some original discoveries, but his monumental effort throughout his lifetime was to prove somebody else right. There's another guy, and I can't think of who it is. He wrote The Black Hole War, and the Black Hole War was about his 35-year quest to prove Stephen Hawking was incorrect on one point of his theory about information in black holes. And it's a fascinating book. And the
Leonard Susskind.
Leonard Susskind. And not to take anything off of him at all, Dr. Susskind, but he basically spent his career, you know, because Hawking said all these things, aha, here's this one place, and I think he's not right. And he spent decades And aha, we've proved it. Really, we often teach science as this great march of progress forward, and we teach science as this people building one upon the other. And I think Karl Popper's idea of science is more accurate. Popper said science is more like, you know, a bar fight cage match in a cheap tavern somewhere off the beaten track. And it absolutely is last man standing. And most professional scientists spend the bulk of time in their career not in original research, but in trying to shoot down the other fella, because this gives you publication credits. And proving someone else was wrong. And the bigger, can you imagine how famous you would be if you proved Einstein wrong about some part of relativity theory? I mean, your name would be, you would be trumpeted by all the media.
Right.
You know, look at the people who made that silly mistake. Pluto's not a planet. And we still hear about them. My biases are showing. Anyway, ultra-diffuse galaxies.
Yes, ultra-diffuse galaxies.
Ultra-diffuse galaxies.
Tell us about them.
So Sandage and Binggeli, and I'm hoping I'm saying this fellow's name right.
Okay.
He's a Swiss fellow. Binggeli, he's a professor emeritus of astronomy and physics at the University of Basel in Switzerland. And they looked at these galaxies, and what they were finding is galaxies which were very, very dim. And they said, oh, gee, why are they dim? Well, they start looking at them and they realize a couple of things. First of all, they're looking at the spectra from all the stars, and they're realizing they're all way over on the HR diagram, indicating they're all very old. And we look in our own galaxy and we say, where do we find really old populations of stars? Globular clusters. Globular clusters. These globular clusters form in the halos of galaxies, and they nucleate, and there's no gas there. There's no star formation there. There's no nebulosity in them at all. And all the spectra indicate these are very, very old. 8, 10 billion almost years old.
As old as the universe, right?
As old as certainly as old as the Milky Way. So these are some of the first population of stars. And why did they form and then cluster in spherical halos when most of the galaxy is lenticular in form? We don't know. But then we look at these ultra-diffuse galaxies, and Sandage and Binggeli are looking at them and they go, holy cow, look at this, it's crazy. All the stars are old. And how do we normally see galaxies? Why do we normally see galaxies? There are a couple of things that we normally see. One is star formation. And the second is gas and dust. And the two things are tied together. The star formation, first of all, star forming regions tend to make large blue stars, which are very, very luminous. They have short lifetimes. They give off light in the blue-violet, ultraviolet region of the spectrum, and they die spectacularly in supernovae in 10 to 20 million years. They don't live long. And the second thing is we look at the gas, the cold gas that feeds star formation. These bright blue stars ionize this gas, and this gas re-emits light in the hydrogen alpha spectrum, the very bright. And the dust reflects this blue light preferentially. And so the dust, the gas, and the forming stars, they're basically like the lights on the Christmas tree. They illuminate the whole thing. The reason we see spiral arms, it's density waves of gas and dust, star formation, ionization, reflection nebula. All these processes are going together and they make the spiral arms glow. The spiral arms are not significantly more dense than the space in between the spiral arms. It's just the rate of star formation there is higher, and so it's more visible. Well, we look at these ultra-diffuse galaxies, and Sandage and Binggeli, they find out that, gee, these things are crazy. The star count is anywhere from 100 million to a billion stars. Somewhere between 1 and 10% of what you would find in a large spiral galaxy. Our Milky Way has a mass of 1 trillion solar masses. We have somewhere around between 100 and 500 billion stars. Call it 500 billion, just a round number. And I think that number is low, and we can talk about why. But essentially, we're looking at these things and we're saying, gee, okay, here's these galaxies that have just a fraction of the mass and a tiny fraction of the star population, but they occupy the same volume as the Milky Way. They're 100,000 light years across. And you're going to say, well, gee, are they a lenticular disk with the bulge in the center and the disk thins to the edge? Hard to tell, because most of the way we see the disk is from dust and gas. And these things have been stripped of dust and gas. That's why we refer to them as quenched. Their star-forming engines have been destroyed. Their gas tank has been siphoned dry. And of course, you start to think, well, gee, if they have no gas and they have no dust, then why not? And the stars show that they are very old structures. And so these dwarf galaxies, ultra-diffuse galaxies, are quite old. And they were around in an era when there was, in fact, more dust and more gas, because less of it had been converted into stars. Less of it had evolved down the evolutionary pathway to white dwarfs and black holes and neutron stars. There should have been more stuff then. So why isn't there any here? Well, sorry?
When they do spectra of these diffuse galaxies, do they find lots of metals? I mean, what are they seeing?
I'm not sure about the metallicity. I'm assuming that they're kind of standard population 1 stars, but I don't know that for certain. I've not seen anything that refers to that in any of the stuff I've read.
I see.
My assumption would be, because they're quite old, that indeed they would be metal rich. The stars would have, and once again, folks, when we talk about metals in an astrophysics sense, we're talking lithium on up. So stars get together, they start fusing, they form helium. Everything above hydrogen for an astrophysicist is a metal. And so what Scott and I are talking about is, are they showing significant deposits of carbon, oxygen, nitrogen, helium, lithium? These primary fusion products from the life of a star before it goes supernova. As many of you know, it takes, you can only go up through iron, atomic number 56. And if you can't go farther than iron, because iron is the last. Once you fuse and make iron, it still gives you energy, but anything larger than iron requires energy to make it. It's no longer an exothermic reaction. And so it won't fuse, right? Iron won't fuse because it requires energy instead of liberating it. So iron doesn't allow the radiation pressure that keeps a star inflated. And once you get to an iron core, the last of the hydrogen helium fusion is done, and stars fuse up, hydrogen, helium, lithium, and they go up through carbon, oxygen, silicon, nitrogen, but eventually nothing more is fusible and the star collapses. You have a supernova. Interesting comparison. If you had 100 million of the largest atomic bombs ever produced, or if you had a ball of TNT the size of the Earth's orbit,
okay,
and you have a supernova is many orders of magnitude above This
So there's
this
no,
amount of
it's
energy. Supernova is just so
like a match strike against,
yeah.
yeah, okay, nothing.
Yeah, it begins to collapse in. It hits an incompressible core, and it all these elements fuse, and huge amounts of energy released, and basically the innards of the star are blown out into the interstellar medium. And so we see this supernova event. These old stars, and you think of old stars in our local neighborhood. Betelgeuse is one, right? So we say, oh, we're going to see red giants, but we also see blue giants, right? Our short-lived stars, ready to go boom. But things that are old tend to be old yellow dwarfs, old white dwarfs, red giants. And we see all stars in kind of the end phases of their evolutionary pathway. There you go, oh, okay, so these ultra-diffuse galaxies, but they've also taken 0.1% of the population and spread it through the entire volume. So you realize you're talking now, the average distance between stars is now 1,000 times what it is in our galaxy. No appreciable core structure. You just have a diffuse, basically an open star cluster that's 100,000 light years wide, containing up to 1 billion stars.
Wow.
It's like an open cluster. It's like the double cluster in Perseus, except it's
almost not there.
It's almost not there, but it's so enormous and very difficult to detect. You're talking, you have to look very carefully, not just in visible light, but in infrared. And you're not going to see much in the short wavelengths because none of that violent stuff is happening. There's no star formation, there's no star birth, there's no ionization of gas. So you're looking primarily in visible and infrared. And these ultra diffuse galaxies, essentially, we think there are one of two outcomes. One, they could be gravitationally ejected. They could be formed inside of a galactic cluster, and they could get ejected. And if they're ejected, they tend to have a very long lifetime, slowly burning out until they just, I suppose they would be something like a white dwarf neutron star black hole cluster, which is kind of creepy as hell. But
yeah,
the galaxy of dead stars.
It sounds like a perfect subject because it's getting very close to Halloween, right? I mean,
it is. It's the ghost galaxy.
Mm-hmm.
But these things are out there. The other possibility is that they may not escape. And if they don't escape, you know Halloween movies, right?
Yeah.
People go into the haunted house alone, and
yeah, you're a teenager, you think everything's good, you're partying.
Right, exactly.
And then the claw comes out.
Right, and then here comes the guy in the hockey mask. And the guy in the hockey mask is a large spiral galaxy like Milky Way or Andromeda or Triangulum. Yeah. We should have a picture of Triangulum with a hockey mask on. When these galaxies, when these small dwarf galaxies, when they go ahead and they have interactions, we think the interactions give us something called gravitational refraction. And I'm going to share a screen with everybody. And I'm going to ask you to stretch your imagination a little bit here.
Okay.
So before we go here, imagine the typical ray diagram we see. It's a classic beam of light, Newton holding the prism in the beam of light, and it gets refracted out into a rainbow, right? Classic painting by somebody or other.
Yeah.
Well, what's happening here? And we all know how this works, right? The speed of light in air and glass is different, and the curved surface of the lens bends different wavelengths differently, and so they spread out, and we separate the colors. And whether we're talking about a rainbow or we're talking about an apochromatic objective focusing light, and we use different types of glass to keep all the wavelengths together. Or if we're talking about a simple single element, why they had chromatic aberration? Because the different wavelengths were bent differently. Well, we take a look at this gravitational refraction. We see this dwarf galaxy, and we have it labeled over here, original dwarf galaxy. And we see the line that continues past this large spiral. And we see that, oh, this is the path of the center of mass. But guess what? Some of the stuff, and this is the essence of the Roche effect, right? Inverse square value of gravity, the stuff that's closer to the big object is distorted more than the stuff that's farther away. And this is exactly the kind of process that makes a ring out of a moon. Well, what we're seeing in this dwarf galaxy, some of the stuff, some of the lightweight, non-compact matter, gas, dust, just gets absorbed by the spiral. That's our red arc here, the red arrow. But other stuff, the compact matter, which has more momentum, the stuff that's closer to the center of the galaxy gets bent more. The stuff that's farther away from the center of mass of the big galaxy gets bent less. And so we have a refraction effect, just like light through a prism. Except this time what we're effectively doing is we're taking a nice compact dwarf galaxy and we're stretching it out. Just like a prism takes a nice compact beam of light and stretches it out and spreads, and we're able to see the spread because, oh, our eyes, our retina detect the different colors. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And we go, oh, well, okay, there we go. Well, here, what would we have? Well, we would have the stuff that's closest in would be the analog to blue light, and then the stuff that's farthest away would be the analog to red light. And they get bent differently, and different pieces get spread out. And so as the dwarf galaxy goes past, it gets stretched. And the folks who are doing this research refer to this as a backsplash orbit. I don't know why the term backsplash. I like my term gravitational refraction much better.
Yeah, it sounds much more elegant.
A backsplash orbit just sounds messy and imprecise. But what happens when you have this kind of pass by of a big galaxy, small galaxy past a big one? First of all, the big galaxy siphons off. Anything that's not nailed down gets stolen. So lightweight material like gas and dust that is not compact matter, does not have a lot of momentum, gets drawn right into the center of the big galaxy and consumed and becomes new stars there. The galaxy gets spread out into a newer volume, and the physical size grows by a factor of 10 or 20. The volume probably grows more by a factor of between 100 and 1,000. The center of mass still occupies the same orbital path. Shoemaker-Levy 9, Scott.
Yeah.
We saw this comet fly past Jupiter.
Yes.
And if you took the 26 major pieces and they were strung out in a line however many thousand miles long, and if you took their collective center of gravity, the center of gravity, the intact comet before the Jupiter interaction, and the center of gravity of all the comet pieces after the Jupiter interaction would have been exactly the same. If you throw a hand grenade or a firecracker and it blows up, the center of mass of all the pieces continues on that perfect parabolic path. It doesn't change a whit. Now, the individual velocity vectors of the different chunks of hand grenade metal, they indeed go all over the place. If we took this calculation for the center of mass of this dwarf galaxy and we plotted it along here, it would be a perfect parabolic or hyperbolic orbit, as the case may be. It would be a perfect orbital path, no problem, but it's disrupted. The massive gravitational field of the large spiral galaxy causes this little dwarf galaxy to be disrupted, essentially the identical process that disrupted Shoemaker-Levy 9 and turned it into a freight train of cometary impact chunks. And we see this on the moon. And we've talked about this in our program, where we've looked at images on the moon and we see crater chains. Oh, 5-kilometer craters that are 10 kilometers apart and they're in a straight line. And you realize, oh, that had to be something gravitationally disrupted by the Earth. Because if it had traveled from Mars, those pieces would have spread out just the way Shoemaker-Levy 9 did, and the impact sites would have been much farther apart. And so you see this same process. You see it written on the moon's face. You see it in Comet Shoemaker-Levy 9, and we've seen it in other places since, and we will see it again. There's a new big comet coming in. It's going to have its perihelion is going to be about 10 AU out, and it's coming like a freight train. It's a great big comet. It's on the way inbound, and it may be gravitationally disrupted on this pass-through, or certainly on a future pass-through. And the center of gravity doesn't change anything. If you take a pile of rocks in your hand and you throw them across the yard, the pile of rocks will expand as they fly across.
Yes, they
But
do.
the pathway of the center of mass of that cluster of rock will be a nice, smooth curve, a perfectly ballistic projectile. And it's just that different pieces of rock are carrying different parts of the total package of momentum. The same thing is happening here. Gravitational refraction spreads out this galaxy. Now, when you siphon off the gas and dust, you quench that dwarf galaxy. No more fusion, no more star formation, no more reflection nebula, no more emission nebula. And so you quench it, you make it darker. And it's not going to get brighter anymore because the materials it needs to strike a light, so to speak, have all been stolen away. And then the stars just continue to age, but there's no renewal process. And the stars are so far apart now. We talked just before the show. It's been found, and again, this is Hubble and ALMA and different telescopes working together, and they discovered a 500 light year wide hole in the Milky Way, right? You remember seeing this article come up through your news feed? Big bubble in the Milky Way?
Yes.
And they figured it out. Oh, look, here it is. What's happening? Well, it's a very spherical shell. They traced back a supernova from centuries ago, and the supernova went off, and the expanding shock wave of gamma rays and radiation pressure and plasma has basically worked like a snowplow, worked like a spherical snowplow, and it's pushed things out. Have you ever seen explosive forming of metal tankage? You ever seen that?
No.
They basically take sheets of metal and they rivet and weld it together, and they know that, oh, if these sheets were all expanded perfectly, that the tank would be a sphere and it looks like a deflated balloon. And then they hang a couple of sticks of dynamite in the center and they cap it off, and boom, and the shock wave, and it's explosively formed into a perfectly spherical tank.
Oh.
If you look up explosive forming of tank.
That's a manufacturing process?
It's a manufacturing process.
Holy smokes, what a fun job.
And so we're seeing this happen in the galaxy, right? Explosive forming. And boom, you get this shell. But the shell isn't important. What's important is that the boundary of the shell is a compressed area of gas and dust from the nova plus whatever was in the interstellar medium. And it leads to new star formation. Okay, but now you're increasing the distance between stars by a factor of 100 or 1,000. Guess what? If one of these things goes off, if a tree falls in the forest and no one's there to hear it, does it make a noise? if one of the things goes off and there's no interstellar medium to speak of, and there's no other stellar region anywhere close, we've all heard the horror story of the supernova that goes off 20 light years away and sterilizes a whole system from the gamma ray burst and neutron burst from the supernova. Anything within 50 light years dies. Okay, well, here you haven't got anything within 500 light years. The star ending its life and going supernova can't seed more star formation because the whole thing is too diffuse. And there's no interstellar medium there anyway. And so you get this interesting process that, yes, we think there are rogue ultra-diffuse galaxies. I believe there are. I don't know that any have been discovered. Let's take something that's ultra-diffuse, ultra-dim, only shows up on a few wavelengths. The Webb telescope or the Roman telescope might be able to see them, but these things are out there. Ground-based telescopes, even the Hubble, can't detect them. They're too spread out, they're too faint. But these, in some cases, you might have a situation where if the gravitational refraction is too intense, you might just basically, like, a dandelion. All the seeds in a strong wind go poof, and it just all explodes and gets completely scattered. We know of some situations where there's a supernova that's strong enough where, in fact, the supernova goes off and you're not left with a neutron star and you're not left with a black hole. It just blows itself completely to smithereens and there's nothing left. So we're seeing what I find interesting is we're seeing this process. And when we talk about Able 2744, we're talking 3.5 billion light years away. And so we're looking at this galaxy cluster, and people think that, it's probably at least 4 other clusters that have fallen in together and merged to make this object from the Able catalog, this mega galaxy cluster. And in this kind of an infalling, how catastrophic would that be? These things infalling over a period of 100, 200 million years, and all the gravitational interactions and crack the whip. And a lot of the smaller galaxies get cannibalized or destroyed, or they're just made into ultra-diffuse. They may be made into ultra-diffuse rogues. They may have kind of like a long period comet. They may have an orbit of a couple of billion years before they infall back into the galactic cluster again. And at which point the galactic cluster will be more compact. So we have to look at these ultra-diffuse galaxies essentially as temporary objects again. We've talked about how rings are temporary, moons are temporary. And it turns out that indeed, if there's nothing new under the sun, well, nothing lasts forever either.
True.
And the lifespan of these, the universe isn't old enough yet for these things to have had its way with these ultra-diffuse galaxies. But we can see clearly from their evolutionary path that what's happening is these things are on the short end of the cosmic stick. They're going to be either cannibalized and devoured, destroyed by bigger companions, or they're going to be ejected out where they may very well lose gravitational coherence and just form a billion rogue star systems just spreading out through the cosmos. It's odd to think that there may indeed be planetary systems where there is no Milky Way. And the sky is not that star-filled like we experience. We experience a star-filled sky because we live in a dense, large spiral galaxy. One of these stars looking out into the night, galaxies may be as common a sight as stars, and the sky may be very black indeed, with just a few points of light in it, and nothing like a Sirius or a Procyon, a close, bright star like Betelgeuse or Rigel. It'd be all really diffuse stuff like Camelopardalis and Lynx and Sagitta, these really faint, tiny stars from far away. A species evolving there might need to develop telescopes before they even knew there were stars in the sky at night, or more than a handful. The idea of stars in the sky being an analog for countless wonder there, oh yeah, there's 9 of them. They would undoubtedly develop an interesting mythology.
Yes.
In their dark and empty sky. So there we go.
There we go. Okay. Okay. Very interesting.
We had a couple of fun books to recommend to people. They're in the chat. One is Einstein's Telescope, The Hunt for Dark Matter and Dark Energy in the Universe, Evelyn Gates. Highly recommend that if you want to understand how these things are detected with gravitational lensing. And then The 4% Universe, Richard Panik, Dark Matter, Dark Energy, and the Race to Discover the Rest of Reality. And we're going to keep on our deep space theme for next week, Scott. We're going to talk about the ideas of dark matter, dark energy, and how do we know we're just 4% of all of reality?
Yeah, how did you come up with that number?
It's interesting to see. The idea that everything we can see is just, that's just a shavings off the pencil.
You know, I think it's long been known that astronomers are only getting to see, such a thin slice of what's really out there, so, that has, it's interesting, the stories of discovery that led astronomers to look at the universe in different ways, in different wavelengths, and to build the telescopes to allow them to do that, whether it was X-rays, radio waves, so it's and some of the images I love to see, Daniel, are images where they have compiled, visible wavelengths with radio and infrared, and it's all piled one on top of the other, and you're starting to get a view that would be impossible for you to see through any telescope or photograph it through any one wavelength or whatever. But that's very interesting. I shared a couple of videos. Actually, they're compiled images. One of them being the Veil Nebula that was released by the European Space Agency, where you could see moving filaments of the Veil Nebula. Another one is a 10-year time lapse of the Crab Nebula, and that's got to be, for me, that's one of my all-time favorite, images, because you can see the inner structure whirling like crazy, and so it's.
Have they ever done that time lapse thing with the Eta Carina, the Homunculus Nebula, where the stars?
Oh, maybe. But
I know that's one that they've been watching for a long time. And
I think they have.
That's evolving in very short time spans, which just fascinates me.
Oh, sure.
It's
animation showing scenario. Now, some of these might be like computer simulations.
Okay.
Let's look at this one.
Okay.
This is images, animation of the massive star explosion. Okay.
Sure.
If I can get there. But it's kind of fun. Just go and, Google.
Go and explore.
Your favorite deep sky
all around
object.
the web and learn stuff.
Right.
Make sure
I'll just share the page where you can see some of this stuff.
Okay.
Here we go. And this is from Chandra.
Okay.
There we go. Yeah, but there's others out there. But can you, the dedication of some amateur astronomer photographing the Crab Nebula for 10 years, okay, with this telescope.
Honey, I'm going to photograph this nebula for 10 years.
That's right. You're crazy. Yes. So
I can
anyhow,
hear it now.
a beautiful result, so. But okay, well, that's great. Daniel, thank you very much, man.
right.
We have coming up tomorrow, we have the 66th Global Star Party. We're going to celebrate. I mean, it's great that Daniel stays somehow, he's following us. Our minds are somehow melding together. But tomorrow is the celebration of the discovery of Cepheid variable stars in M31, what was considered to be the spiral nebula, the Andromeda spiral nebula, and Edwin Hubble.
For a standard candle,
right? He was able to see, oh wow, these are stars in this nebula, and therefore this is not a nebula anymore. This is an island universe of stars, and so that's very fascinating. We've got Dave Eicher from Astronomy Magazine, who devoted a beautiful book to galaxies, and he's going to have an extended lecture on there. We will, looks like we're going to have Molly Wakeling on. Gary Palmer has agreed to show us images of M31 done with an amateur telescope that should show the Cepheid variable that Hubble discovered all those years ago in 1923. And this is kind of a surprise, all right? But and I don't have a confirmation yet, but Mount Wilson may jump in here, and that's where this was done. Okay, so if they come on, they plan to show something very special. So anyhow, we hope that you watch it tomorrow. It starts at 7:00 Central. Tuesday night tomorrow, and you can help us celebrate this very auspicious time, because the universe went from 100,000 light years in age and diameter or whatever to now millions and then billions with Sandage's work, billions of light years, right? So
right, we're all following in the footsteps of Copernicus. He's the first one that blew up the universe, because at his time everything ended right after Saturn. There was the sphere of stars, and then that's where God lived. And Copernicus said, no, the Earth is a planet, the sun is a star, and all the stars in space. And of course, Bruno died. Giordano Bruno, the monk, 1600, he's executed by the Inquisition for saying Copernicus was right. And it's called the many worlds hypothesis, the idea that all the stars in the sky are star systems with planets. And I think a future program for How Do You Know, I'm going to keep in mind the distance ladder. How do we tell how far away things are? And we've developed a whole series of mechanisms. And one of the very first ones, of course, was parallax. And stellar parallax for a long time was used as an argument against Copernicus. Well, if we really orbited the sun, that's a huge baseline. We should be seeing parallax. And Copernicus said, no, it's just that the stars are really far away. And everybody laughed at him and said, the world's not that big. But every group that's tried to say the cosmos is this big and no bigger has taken it in the neck. Yeah, they've been knocked
once
off,
you think you've got it all figured out, just figure this. You're probably
Copernicus,
wrong.
The Copernican principle of as soon as you think it's small, unique, limited, you're wrong.
Yeah.
And the same way, I think dwarf galaxies tell us our estimate of the number of galaxies. Wrong, way low. Red dwarf stars tells us the estimate of the number of stars in a galaxy. Wrong, way low. And I think that we're going to see. We continue to see this. It's been a trend throughout my lifetime. I don't see it stopping now.
Oh no, it's going to
space
probably
is big, really, really
accelerate as we get older here. So
yeah, exactly.
That's right. Yeah, that's very cool. Anyways, we really appreciate our audience watching today, mostly on YouTube. I think maybe only on YouTube. If you do like to watch us on Facebook, we're sorry that they had their outage, but I imagine they'll get that fixed probably, hopefully tonight. So let's see what happens.
Indeed.
And until that time, keep looking up, and we will see you tomorrow. Take
See
care.
you next time. Bye-bye,
Yeah,
everybody.
take care. Bye-bye.
Hi, this is Dave Eicher. This coming week marks 98 years since Edwin Hubble discovered the nature of galaxies and the cosmic distance scale. To celebrate, join me for a special talk on galaxies this week on Tuesday night, October 5th, on the Global Star Party, brought to you by Scott Roberts and Explore Scientific. I'll see you there. Happy stargazing.
Hi friends, Vivian White here from the NASA Night Sky Network, and I just want to invite you all to join us for the Global Moon Party happening October 9th from 3 p.m. on, that's Pacific time, 6 p.m. Eastern time. We are going to have such a blast. We have great folks from the International Observe the Moon Night joining us. We have NASA friends from the Visualization Studio and moon treks and all over the place. We have Icelandic poets to talk about the moon, presenting new work that they're doing. Space agencies from around the world will join us, and we hope you will too. Please get the word out. Let everyone you know who loves the moon know that we are kicking off the International Observe the Moon Night this October 9th. See you there.
Hi everyone, this is Terry Mann, and I'm the Secretary of the Astronomical League and the co-host of Astronomical League Live. We have a special event coming up on October 15th at 7 p.m. Eastern Daylight Time. We're going to have a kind of Halloween party online. We have quite a few speakers. The first one is one of our regulars, one of our favorites, David Levy, and he will be doing celestial incantations. Next up, we'll have Mary Stewart Adams, Passing Between the Worlds Under October Skies. We've also got Astro Bob, Black Holes Where Matter Goes to Die, and Molly Wakeling, Spooky Nebula of the Night, and John Goss, the Master of Lunacy, and we do expect that name to stick. Barbara Harris, Algol, the Demon Star. Myself, Aurora, Soul of the Night. And we've got Carol Orge, the president of the Astronomical League. We're going to put a wizard hat on him and let him work his magic. So please let me personally invite you to join us October 15th, 7 p.m. Eastern Daylight Time, right here. We hope to see you.
Why do we chase this thing? Jumping from one continent to the next, just to bathe for a moment in the absence of light? Who are we? What are we searching for?
T.S. Eliot wrote, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time."
One of the qualities of seeing an eclipse is it makes you understand that every given thing is in a particular patterned relation with every other thing.
It gives me a sense of scale, gives me a sense of where I fit into the universe.
It is art, it's poetry, it's this kind of experience of going and seeing totality in which what feels merely metaphorical is suddenly experiential encounter.
Immediately afterwards, you have that overwhelming desire to see another one. That's the moment an eclipse chaser is born.
These are folks who are running all over the world for this event that lasts all of 2 or 3 minutes. Who are these people?
It's unique each time. And therefore that freshness, even if we've seen it over and over again, oh my gosh, it has the potential to re-inspire us.
A total eclipse of the sun doesn't just unfold in the heavens. It transforms the minds and hearts of those who experience it firsthand. The same is true of journeys to the most remote regions of our planet. Whether we're standing on a mountain peak or in a stark polar landscape, we can't help but reflect on our place within the larger scheme of things.